Hello, hello. This is another example from communications. We are going to look at the labeling the digital to analog conversion block, ADC, DAC block. All right, so let's go. So here it talks about the digital or transmission of speech. It can be illustrated in the block diagram below. Okay, so first state what is meant by a digital signal. So you can refer this to your notes, but this one is a signal consisting of a series of highs and lows, ones and zeros, on and off. Okay, so I'm just going to stick to ones and zeros to remind ourselves of the binary code. Okay, state the names of the component labeled X and Y. All right, so you just flip it opposite law. If this one is ADC, this will be DAC. So you can call this the DAC. Or if you are feeling paranoid, you can call this the digital to analog converter. Okay, so again, X will be the opposite of Y. Sorry, X will be the opposite of this box. So if this is serial to parallel, this one will be parallel to serial. Bonus. Okay, because what we're doing is we are reversing what we have done to the signal from analog. After the sampling, we will get a bunch of ones and zero. And then here we want to stitch back to get analog. All right. So part 3, describe the function of an ADC. So the ADC, remember, if you remember the previous video series, what we will do is we will take the sampling frequency, we will sample the wave at different intervals. So you could say that the analog signal is sampled at regular intervals. So we're just describing what some of the things that you will do in the past year question. So analog signal is sampled at regular intervals and converted to a digital number. And this digital number is binary lah. Okay, so all this is pretty general and facts lah that you should kind of memorize based on this block. Moving on to the next part, part B. The optic fiber has a length of 84 kilometers. I'm just going to roughly draw out an optic fiber or a line to represent the optic fiber. And this optic fiber is pretty far, 84 kilometers, with the attenuation per unit length of 0.19 decibel per km. So this means when you travel every kilometer, the ratio of your intensity drops by 0.19. The input power of the optic fiber, so I'm going to draw it here. This is P in. Input power is 9.7 milliwatt. At the output of the optic fiber, the signal to noise ratio is 28 decibel. So at this point here, the output, I don't know what this P out is, the output signal, but I know that the SNR is 2.8 decibel. Okay, part 1. Calculate in decibel the ratio of input power to optic fiber to noise power at the output of optic fiber. Okay, so let's see what they want first. They want input power, and in decibel, so we're going to have to do the 10 log thing again. All right, in fact, everything in this part of the question is always 10 log and then a ratio. All right, so now what they want is actually 10 log the ratio of the input power over Pn, n here for noise. Okay, so input power against noise. Of course, you may be wondering, Miss, we don't have the noise, but we have the signal to noise ratio at the output. What is this 28 dB? This 28 dB is actually equal to 10 LG signal. So P out over PN. And here is noise. Okay, so there's some noise on that side as well. Okay, so here I have summarized the question in a handy dandy drawing, so I got more space, right? You have the attenuation per unit length along the 84 km optic fiber. This means that the intensity of the input signal will attenuate or will drop. If it helps you, you can always sketch a graph if you're a very visual person. No harm there, so I'm just going to sketch out a graph or a rough drawing. Okay, so this power signal, I know P in, sure. P in is 9.7 milliwatt. This is power. The power is going to drop until here. I'm not sure what P out is. This is P out. Okay, and you are asked to find what is the ratio of the input power to noise. Okay, so I will show you the normal way, which is not the way they expect you to do. They expect you to use the smarter way or the faster way. Then, if let's say, and then I'll show you the second method. If you're okay with the second method, it is shorter, it's easier to use, but you need to know some background about log and lon. Especially this identity up here. Okay, so I'll show you both methods. Now, in this case, right, we want to find input to noise. So we need two power values. We need the input, which we already have, and we need the noise, which we don't have. So we're going to find the noise power. What I know about noise is that the signal to noise ratio is 28 decibel here. Okay, so I'm going to use this one to find the noise power. Okay, so I will write here method 1. Step 1, I will find the noise power. Find P noise. All right, so I know that the signal to noise ratio is 28 dB. So 28 is equal to 10 log signal. So this is the P out over PN for noise. But we kind of have a problem because we don't have P out. So we need to find P out first. Miss, we can find P out, right? Because we have the attenuation per unit length. Okay, so by the time you reach here, you go like, I need to find P out. So this will be now step 2. Okay, so I'm just gonna move this a bit. So actually, step 1 is to find the output power. Okay, so I know the attenuation per unit length. Attenuation per unit length is 0.19 decibel. Okay, in order to find the attenuation, we will take 10 log P. Okay, you have to be careful here. So if this is going to be positive, right, meaning we'll take the bigger number, which is P in, divide by the smaller number, which is P out. So this would be 0.19 for 1 km, but it travel 84 km, so multiply by L. Bring the L up to multiply. This is 84 km. Okay, so obviously we can use this to help us find our P out. All right, so I'll do that now. So I'm just gonna, I've showed you how to press the calculator using the previous example, so now I'm not going to do that now. I will just quickly find the value of 10 to the power of 0.19 times 84 divide by 10. So log P in, not log, I anti-log. So P in over P out is 39.445. So maybe I'll put 39.4. 446. Okay, and now I can find P out because I have P in, right? So the input was 9.7 milliwatt. So 9.7 times 10 to the power negative 3 divided by, bring over 39. You can put 39 also if you want. I just want a bit more accuracy. Okay, so 9.7 negative 3 divided by answer. So this will be 2.46, 2.49 times 459 times 10 to the power negative 4 watt. So in this case, whenever I reach here, this value here is 0.246. So this is power in milliwatt. Okay, so the power will drop a lot actually. Drop almost 40 times. Okay, so whenever you get this value, now you have P out already. So now step 2, we can now find P noise. So this is what I mean by long, not wrong, just long. We have the output. P out is 2.46 times 10 to the power negative 4. We want to look for P noise. Okay, so let's see. I can just press my calculator, okay? So what I'll do is I will anti-lock. Actually, I should show you how I press so that you don't get stuck too much in this, spend too much time. Okay, 10 bring over and divide. So I will anti-lock. Anti-lock, which is 10 to the power of 2.8. Okay, so this number is the ratio of output over noise. I want to find noise, okay? So I will take 2.46 e to the power of negative 4 divided by answer. This, or you can divide by 631 if you want to. Okay, so I have the noise power 3.89. I guess 3.90 times 10 to the power negative 7. Okay, so 3.90 times 10 to the power negative 7. Generally, you leave to 3SF is good enough. This is just me being extra. Okay, don't worry about it. So once you have your noise, then finally you can get your answer already. Because what were they looking for again? We want input to noise. So hence, the ratio of input to noise in decibel will be equal to 10 log P in over P noise. So finally, we got everything. All right. Your in was, what was it again? Starting one. 9.7 milliwatt. So this will be 9.7 times 10 to the power negative 3. And your noise was 3.90 times 10 to the power negative 7. Okay, lor. So we press calculator again. All right. So 9.7 divided by 3.9 negative 7. Okay, so I get 43.95 or 96, which is approximately 44 decibel. So this is actually a multi-step process. I would say it is a 3-step process. Just many things to do. So we started off by wanting to find the input to noise ratio. And then we noticed that we got input, we don't have noise. So first we wanted to find noise, but we noticed that because it's the signal to noise ratio, this is the SNR 28. I don't have the output signal value. So I have to find the output signal value using attenuation per unit length. So the input is 9.7. I know every km will attenuate 0.19. So the cable is 84 km, I multiply by 84, and then I anti-lock and find the value of P out. And then from here, I find the value of P noise. Because I got the signal to noise ratio, I already have P out, then I can find P noise. Once I find P noise, I can put inside here. Very nice. Very nice. Okay, this one like a lot of work leh, miss is only 2 mark. 有没有搞错? Why like this one? Okay, so they don't expect you to do this. There's a reason why they log in the first place, so that your brain doesn't hurt so much. Doesn't have to find this to find this to find that. Okay, so what do I mean? Okay, so maybe if we zoom in a bit and we think about what is happening. When we travel from here to here, there are a few ratios. Okay, the first ratio I have is the fact that this P in and P out will not be the same. So 0.19 decibel per km. So the first ratio that I have, first one, is that the attenuation, which is 10, depending on what you want to log lah. Okay, let's say I log out over in. You want in over out also can, but I just want variety. So if out over in, out is smaller, then this out is smaller, right? So you should write negative 0.19 times 84. Okay, and when I multiply this, I will get 16 decibel. Okay, 0.19 times 84. We did this before, it's here. Okay, so the attenuation out to in is negative, and then just for you again, highlight and I write in red lah. Who knows, maybe 1 month later you stare at this, you don't know why I put negative. Put negative here because output is greater than input. I didn't put negative here, this is positive because P in is on top. Okay, so P in on top, the bigger one is on top, then it's positive. The smaller one is on top, then it's negative. Okay, you go and press lock and see lah. If let's say I lock 0.999, I'll get a negative number. See? If I lock, the ratio is more than 1, I'll get a positive number. No? Okay, so it depends on the ratio. Anywho, this will be negative 16 decibel. Alright, keep that in mind. Alright, so the other ratios that we have include the SNR ratio. SNR at the output. Okay, so if you think about the signal to noise ratio at the output, it is actually 10 log P out over P noise. Noise here is constant, okay, is equal to 28. And then you are like, miss, how to get this input to noise? I got output to noise. Well, there's this thing called the chain rule, right? So I can break apart this 10 log, okay? I can split this P out multiplied by P noise. Okay, let me scroll up so it's not beside my face. Okay, so divide this. Chain rule, guys. What do you want? I want P in over P noise. So I'm going to put P in here. Claim what I want. I want input over noise. Then you put P in here. Lor. These two P in will cancel out, ma. So it's as if you didn't change anything, right? Correct? I'm going to open this. Okay. So when I open this, I get 10 log. So this is A plus B. Log A times B. No. Write the identity here. Log AB is log A plus log B. I label the AB for you lah. Those of you who don't do mathematics. This is my A. A. And the other one, this one, is my B. A times B. Okay, so then, I do slowly. So this will be P out over P in plus log P in over P noise. Okay, there we go. Ding, ding, ding. This is 28. Okay, so if that's the case, right, now you will open this. This is 10 log P out over P in plus 10 log P in over P noise is equal to 28. My friends, family, children, Gai Fong, we want input over noise, but we have the attenuation. Okay, not sure if you noticed this, but this 10 log P out over P in is here. Ooh, we have this. It is negative 16. This whole thing is your attenuation, which is the second reason why they are doing this, attenuation. So this will be negative 16 decibel plus, this is what we're looking for, the signal to noise ratio or the input to P noise at the start of the cable is equal to 28. So hence, the ratio of input to noise in decibel is equal to 28 plus 16, which is 44 decibel. Ta-da! Ta-da! So this is what they mean when you write, you know, when they ask you, why must we use log? Why must log here, log there? Why can't we just go and find the output power? You see, so tired, leh. You have to go and find this power, then you have to find this power, then you have to go and find this and ratio again. So the strength of using log, although you may not feel that way because you are not yet comfortable with the log sign, is that when you use log, you can just write your working this way. You don't even need to prove. This is me proving it to you only. But once you get a hang of it and you understand that log A times B is log A minus log B, then what you can do to yourself is, if I want to find the input to noise ratio, right? So I know that there are a few ratios happening here. Okay, I'm just going to show you. This is 28 decibel. Okay, and then the attenuation is dropping at 0.19 decibel per km. So when you travel down here, totally you will minus 16 decibel. At this point, you are 28 decibel. So then this point, 44 lor. Because 44 minus 16 is 28 ma. Okay, so 44, when you minus 16 decibel is 28. So this is actually what they want you to do. Okay, so I don't want you to just plus and minus and then you yourself are not sure what is going on. If you need to, it's okay to go through this process, and then go through this process, you think a bit long, like a bit pain to press the calculator. And the benefits of using log here is that we can use the idea of the fact that we have the attenuation. So because of chain rule, we can just plus minus the attenuation accordingly. All right. So hopefully that part is helpful. I will transfer the working over. But one last thing I want to mention to you is that we know the noise. Let's say this is the noise. The noise is so this is P noise. P noise is constant one. My constant line is so not constant. Apologies. So very tiny. This is my P noise. In fact, my P noise shouldn't even register here because it's 3.9 times 10 power negative 7. Okay, so there are a few ratios. The first ratio, attenuation per unit length, is 10 log 9.7 and P out. Second ratio is 9.7 to noise, PN. Third ratio is output to noise. Because they have the same noise, that's why we can do the chain rule to cancel it out. Okay, so hopefully that is clear. All right, always think about your decibel as ratio. Depending on, ratio is your best friend, but this ratio is now on steroids. So depending on your comfort level, it's okay to budget some time to look for this, okay? But in the nutshell, they just want you to write something like this. Because at the end of the day, when you use A times B, the chain rule, it will look like log A plus log B. And we know that technically speaking, you start with 44, you end with 28, and every km you drop 0.19, so 84 km you will drop 16. That's why we can minus. So of course later, if you only study communication and you don't care about the maths behind it, then we will just tell you to minus. But why can we minus like that? Can you just simply minus? Can, because log allows us to do this because of this law, A times B. If not log, then cannot log. So that's why we can just add addition. So for working, what they expect you to write is actually something like this. You will take this one would be 28 plus, or I guess maybe they will ask you to find the attenuation, which is equal to 84 times 0.19, which is 16 decibel. And then, hence, 10 log P in over P noise, this ratio will be equal to, you travel to the end is 28, so you need to plus back the 16 to get the input, which is 44 decibel. All right. Next, the noise power at the output of the optic fiber. So if you did method 1, your answer is already there. You just transfer over here. But since assuming I didn't do method 1, I just did this. So I know the signal to noise ratio. And right now, I can say that 44, this is the input, correct? So 44 is equal to 10 log. I have the input 9.7 milliwatt, -3. Your milliwatt, okay, -3. And we're looking for P noise. This is also a nice time to double check your answer. Okay, let's press calculator, the red leaf. I will take 10 to the power of 4.4, okay, and equal. And then I want to find P noise, that will be 9.7 milli divide by answer. 3.86. I guess 3.9. Alright. Because they put 2 SF, the power 9.7. So P noise is 3.8, 3.86, 3.9 times 10 to the power -7. Okay. 3.9 times 10 to the power -7. What? Wow, miss like this 3 mark. Apparently, yes, no. But you want to be safe, okay, I will show you where the marks is. You find the attenuation, this is C1. Answer is A1. You ratio correctly. This is C1. Okay, remember, I always take the bigger number divided by a smaller number because I don't like negative number. But if you flip it, then this thing will be negative. Okay. The other C1 mark is actually, I don't know why, but they want this. I guess if your answer is correct, then you don't write this, also you can get full mark because how else will you get? So this is the ratio of any power P2 over P1. So writing this equation is actually C1. All right. And then the final answer is A1. We can now double check our answers based on this because I didn't use 44 to find the noise power. All right. If you look here, what did I do to find the noise power? I use the signal to noise ratio at the output, which is 28. Just now I used 44, which is the signal to noise ratio at the input, because I don't know what's the output Okay, using that method, I don't know what's the output, didn't find. So my answer is the same, so that is great. Okay, so that's how you can double check your answer. But I generally think it's not needed. So just make sure you are aware, especially when it comes to question like this, that because of the decibel, and we take a log 10, okay, I spent some time proving for you, but the whole idea is we start at a certain ratio and we end at the ratio of 28. Because of the identity of log, where log A times B is log A plus B. So that's why I can plus -16 decibel to reach 28 decibel. Okay, so this is also why they only allocated 2 marks because they don't expect you to go through the first method that I did, where I go and painstakingly go and find the power value for each single thing. So hopefully that process will help you remember why we want to 10 log the decibel. Because the numbers are easier to handle. 44 is nicer than something -7. And because you can plus and minus the ratio easily without involving larger numbers. All right, so that's it for this example. It's a pretty easy one. And this chapter, although a bit of a pain to study, can actually give you good marks if you're well prepared for it. All right, I wish you the best in your papers, and I will see you in the next one. Study with a friend. Click like, subscribe. I will see you. Bye-bye.